This is Mirror's Edge. Developed by DICE and released in 2008, the game garnered a lot of attention because of just how different it was from most AAA games of the time. In an era where online multiplayer games were exploding in popularity, particularly first-person shooters, it was odd to see a developer like DICE, which is known for the massive Battlefield series, create a project so small and focused. Despite being a first-person game, Mirror's Edge's primary gameplay focus is on movement, not shooting. The game was inspired by the chase scene in the opening of 2006's Casino Royale, and was arguably the first game to introduce the sport of parkour to the gaming public. Despite the game's uniqueness, its focused design, beautiful art direction, and stellar core gameplay, we haven't seen any spiritual successors to Mirror's Edge. Many games that came after would only cherry-pick mechanics from Mirror's Edge, games like Titanfall and Dying Light. Now, over 15 years later, the only other game like Mirror's Edge is its sequel, Mirror's Edge Catalyst, and with the way the gaming market is today, we are unlikely to get any other games like it. From the AAA game industry, anyway. There's a plethora of indie games with a focus on movement and quick traversal. A recent parkour game to find success is Rooftops and Alleys, which has seen tremendous support. But to me, these games still don't scratch the itch that Mirror's Edge left for me. So I'm going to do it myself. My name is Benjamin Nelson, and this is the first entry in my devlog on a true spiritual successor to Mirror's Edge, with the working title, Plantigrade. Let's begin. First, I needed to choose a game engine to work with. While I initially started learning game development on the Unity game engine, due to changes in their monetization structure, I decided to go with Unreal Engine 5. This is also a good fit since Mirror's Edge was made in Unreal Engine 3, so I know that the tools I need to make the game I want exist in this engine. I'm also using Unreal's blueprint system to program my game, instead of C++ or C#. This is because there are a lot of resources and tutorials in Unreal Engine that use blueprints, and it's a skill I need to develop. I also wasn't too worried about the limitations of blueprints, since I'd seen that other high-quality indie projects were programmed with it. It also makes it much easier for my audience to follow. I first started with a basic third-person character template, since the player is fully modeled in that template. Then I adjusted the camera boom length and parented it to the head bone on the player skeleton. I made some adjustments to the field of view, and made the player match the rotation of the camera on the Z-axis. With that, I had the most basic form of my player character finished. But this still doesn't feel right. Movement in Mirror's Edge had a sense of weight. The player would accelerate as they continued to run, only reaching max speed after 8 seconds or so. This is when I first learned about timelines in Unreal. Timelines let you reference data along a curve, usually with the X value representing the elapsed time. This means that I can use a timeline to store an acceleration curve that will modify the player character's movement speed. The default speed is 400 units, and the top speed is 750 units. Over a period of 8 seconds, the speed value will increase along the line until the max speed is reached. Now I just add the timeline to the existing movement logic, and set the max walk speed to the output wide value from the timeline every frame the player is moving. When the player stops moving, I set the timeline time back to 0, which resets our speed to default. And when the player is in the air, I pause the timeline so that the player only accelerates while on the ground. We'll now slowly accelerate to max run speed while moving. Next, I added the sidestep. In Mirror's Edge, if the jump button is pressed while the left or right directions are held, the player will do a quick sidestep in that direction. The sidestep is great for use in combat, making a quick 90-degree turn, and can be used to instantly reach max run speed. Implementing this into my player controller was very simple. Before I could add the sidestep, I first needed to implement an enumerator that managed the player's movement state. Different movement states means different behavior. Some of the states that I have are walking, crouching, sliding, and wall running. To manage switching between different movement states, I created the setMovementState function. The function will not change the player's movement state if the movement state they want to transition to is the same as the one they are currently in. So if the player's current movement state is walking, it cannot transition to walking again, only to a different movement state. If the new movement state is not equal to the current movement state, The function will then transition the player to their new movement state and call the appropriate start function. Any logic that changes our player's movement state will use this function. With movement states implemented, I can now get to work on the sidestep. Here's how the sidestep works. Whenever the space button is pressed, the code checks to see if our current movement state is walking. Then it checks if our sidestep is on cooldown. Should both checks pass, an impulse force is then applied to the player in the direction they wish to sidestep. If they're holding the A key, it will be left, and if they're holding the D key, it will be right. Next, the run ground acceleration timeline's current time is set to 8 seconds, using the set new time node, which will put the player at max run speed. Finally, the sidestep is placed on a short cooldown. With that, I had my basic sidestep implemented. Next, I implemented the quick turn. Once again, timelines came in handy. The quick turn code first starts by checking to see if the current movement state is walking. If it is, then it plays the grounded QT timeline, which has the shape seen on the left. The timeline's output value is passed into a lerp node as the alpha, which will lerp between the player's initial yaw rotation and that rotation minus 180 degrees. The resulting value is then applied to the player's rotation. Here's how the resulting quick turn looks. The quick turn can also be performed while in movement states other than walking, though the rotation direction and amount differ depending on the movement state. Next, it was time to implement crouching and sliding. To do this, we need to implement a special function called resolve movement state. Resolve movement state is used to prevent the player from uncrouching when there's a ceiling above them. It's also used to set our movement state back to one of 3 default movement states, being walking, crouching, and sliding. The function first performs a line trace from our player's feet pointing upwards, with a length equal to our player's standing height. The code uses this line trace to check to see if there's enough room above the player for them to stand. If the line trace doesn't hit anything, then there's room to stand, and the player's movement state is set to walking. Otherwise, the function checks the player's current horizontal speed. If the player is moving quickly, the movement state is set to sliding, otherwise it's set to crouching. With this function implemented, I then moved on to the crouching logic itself. My crouch logic is fairly simple. There's a crouch start event and a crouch end event. The crouch start event plays the crouch timeline, which has the shape seen above. The resulting value is then passed into a map range clamped node, which appropriately scales and clamps the value between our player's standing height and crouching height. The resulting value is then assigned to our player's capsule component half height. The crouch end event runs the same logic, only it plays the timeline in reverse, which makes the player's capsule component grow back to its original height. Here's the crouch in action. I release the crouch button here. Notice that the player doesn't uncrouch until the ceiling is no longer above me. Next, let's go over how my camera works. The camera system uses 2 different rotations: control rotation and actor rotation. The control rotation handles camera movement. You can think of it as moving the player's head, whereas the actor rotation is responsible for the rotation of the player's body. By default, the use controller desired rotation boolean is set to true, which makes the actor rotation match the control rotation. If the use controller desired rotation boolean is set to false, then the 2 rotations act independently of each other. I'll be linking and unlinking these 2 rotations together, depending on the player's movement state. From this point forward, I started using 2 special vector equations, the dot product and the cross product. Let's first go over how the dot product works. When you find the dot product of 2 normalized vectors, that is, vectors that have a length of 1, the resulting value will always be between -1 and +1. If the 2 vectors are perpendicular to each other, the dot product will be 0. If they are pointing in opposite directions, the dot product will be -1. And if the 2 vectors are parallel, the dot product will be 1. Essentially, we can use the dot product to find how closely 2 vectors point in the same direction. Now for the cross product. When you find the cross product of 2 normalized vectors, again, those are vectors with a length of 1, the result will be a vector that is perpendicular to the plane created by the 2 original vectors. I'll be using the cross product to calculate directional vectors. With that preamble out of the way, I can finally go over my slide logic, which will be driven by two events, slide start and slide end. One thing to note, every time my code calls slide start, it also calls crouch start. Likewise, every time slide end is called, crouch end is also called. I did this because I could reuse the crouch logic to handle the player's capsule collider height while sliding. The slide start event triggers, naturally, whenever we begin a slide. The first thing that is done is the player's ground friction is lowered so that they can slide around the ground a lot easier. After that, the actor and control rotation are uncoupled. This will allow the player's head to face in a different direction than their body. Some basic camera tilt is then applied. Then, the slide loop timeline is played. This is a looping timeline, meaning that any code connected to the update pin will continuously run every frame until the timeline is stopped. The timeline itself doesn't hold any curve information. I'm just using it instead of a coroutine. Moving off the update pin, the following code is run every frame. The player's control rotation is clamped within a window relative to their actor rotation. This window represents the amount that the player can turn their head without turning their body. A slide force is then applied to the player in the direction they're sliding. The strength of this force is dependent on the angle of terrain the player is sliding on. I'll go more in depth about how this force is calculated in just a moment. After the force is applied, the player's current speed is clamped to their max slide speed. Finally, a check is made to see if the player is moving fast enough to continue sliding. If they aren't, then the slide is cancelled. Now let's go more in depth into how our slide force is calculated. The slide force is dependent on the downhill directional vector of the terrain the player is sliding on and their rotation relative to that. First, the downhill directional vector needs to be calculated. This can be done using the cross product. First, we find the cross product of the world upward vector and the normal vector of the surface we're sliding on. From the perspective of this 2D diagram, the resulting vector would point out of the screen. We'll call this vector v3. Next, we find the cross product again, this time using v3 and our surface normal vector. The result is a vector that points in the downhill direction of our surface. We'll call this vector vd. We're halfway done calculating our force vector. Next, we find the dot product of our downhill vector and our player's forward vector. The resulting scalar will determine the strength of our slide force. The player will slide quickly when sliding downhill, and will slide slowly when sliding uphill. We then take the resulting scalar, which ranges from -1 to +1, and we multiply it by a slide force scalar. This scalar can be any constant that I want. It could be like 1000, for example. The result is our slide force, which we apply in the direction the player is facing. Now let's go over the slide end logic. First, we reset our player friction back to normal. Then, we pass the player's current speed into the inverted ground accel timeline. To understand why this timeline is needed, let's go over the problem that it solves. While the player is sliding, their running acceleration is paused. However, sliding gradually decelerates the player. So I was running into the issue of the two accelerations being desynced. For example, let's say I'm moving at a speed of 750 and I begin to slide. As the slide continues, my ground speed decelerates to 500 units, at which point I stop sliding and begin running again. The expected behavior is that we will begin running at 500 units and gradually accelerate back to our max speed of 750 units. Instead, as soon as the slide ends, the player instantly accelerates back to max speed. This is where the inverted ground accel timeline fits in. It's identical to our run ground acceleration timeline, only that the x and y values are swapped. While the run ground acceleration timeline would receive a time in seconds and output a speed, the inverted timeline receives a speed and outputs the time needed to accelerate to that speed. This means that both timelines feed into each other. And by passing the result of the inverted acceleration timeline into the normal acceleration timeline, the result will put the acceleration timeline at the time that corresponds with the current speed. This fixes the speed disparity that occurs when a slide ends. Now all we have to do is recouple our camera, stop the slide loop timeline, and resolve our movement state. And here's the slide. The slide will automatically transition to a crouch when the speed gets low enough, can be used to quickly move under obstacles, decelerates quickly when sliding uphill, and decelerates slowly when sliding downhill. Now it was time I added something a bit different. In Mirror's Edge, you can springboard off knee-high objects. This gave you a ton of height, but was entirely contextual. You could only springboard off specific props. It also has an animation that briefly removes control from the player. I like the springboard, but I want movement in my game to be more free-flowing, cutting out as many animations that remove control as possible. So I implemented springboard differently. So, how does my springboard work? The springboard will trigger if the player jumps up onto a platform and then immediately jumps again. The second jump will send the player much higher than the first. However, the springboard will only trigger if the platform the player jumps up onto is around knee height. In order to evaluate the condition for the springboard to trigger, I'll need to save the player's transform Z value when they first start their jump and when they land their first jump. Then I'll compare the difference between the two Z values. Should the distance between the two values fit within the correct window, I'll then set the can springboard boolean to true, and then after a short amount of time, set it back to false. Should the player jump within this window, they will perform a springboard jump, which will carry them extra high into the air. With this implementation, we get a fairly versatile springboard that can be used on virtually any object, as long as the height requirement is met. However, there's a bug that needs to be addressed: the ability to perform springboards consecutively. From a physics standpoint, consecutive springboards shouldn't be possible, because the momentum from the initial jump carries on into the springboard jump. So consecutive springboards don't make any sense, since there's no vertical momentum to carry into the second springboard. I was originally going to fix this oversight, but I decided not to. I figured that the emergent nature of the interaction complemented the free-flowing design I was going with. I can already see players finding creative paths using level geometry in unintended ways, and while it is less realistic, realism doesn't necessarily make something fun. With the springboard implemented, I then implemented different landing types. I have 3 different landing types: one from a fall of a lethal height, which will kill the player, one from a fall of a damaging height, which will cause a hard landing that deals damage, and landings from a fall of a safe height. The type of landing is determined by the player's fall speed. If it's greater than 1800, then the fall will be deadly. If it's 1500, it'll be a damaging fall, and anything below that will be a regular fall. Hard landings will damage the player and briefly lock them into the hard landing animation before they can begin moving again. While the animation is playing, the camera will match the player model's head rotation. To ensure that the camera transitions smoothly between the control rotation and the head rotation, I used a timeline in conjunction with a rotation lerp. The timeline roughly has the shape seen here. The lowest Y value is the control rotation, and the highest Y value is the head rotation. As the animation plays, the camera rotation moves along the curve, towards the head rotation, and then back to the initial control rotation. The result is this nice smooth transition in and out of the animation. The logic for deadly falls uses the same method, only instead of playing an animation, we cause the player to ragdoll and the screen to fade to black. With all 3 landing types implemented, I then moved on to implement the roll, which functions identically to the one in Mirror's Edge. The roll is used to break the player's fall and maintain their momentum. My roll works by firing a line trace below the player a short distance whenever they press the crouch button while falling. Should the trace collide with the ground, the roll queued boolean is set to true. While this boolean is set to true, the roll will automatically be triggered whenever the player lands. When the roll is triggered, the player doesn't take any fall damage and the roll animation is played. The roll queued boolean is also set back to false. I also used the same camera blending method found in the hard landing and lethal falls. It should be noted that the roll doesn't prevent you from dying from deadly falls, it only prevents damage from damaging falls. I had a pretty decent character controller at this point, but I still needed to add a lot more. The next thing I implemented was wall running. I won't go into too much detail about this implementation, as the video is getting long enough, but I will give a general overview. My wall running logic is divided into 4 sections: the wall run/climb check, the wall run start function, the wall run movement tick function, and the wall run end function. Let's go over them in the relevant order, starting with the wall run/climb check. The wall run check is used to determine if a wall run should be initiated. This is determined by a number of factors. First off, this check only triggers if the player is in midair and isn't falling too fast. The check occurs every frame until the fall speed threshold is crossed, then it stops. The check first starts by firing a line trace starting from the player and pointing in the direction that they want to move relative to their camera. If the player is holding W, the line trace will shoot directly in front of them. If they're holding W and A, it will shoot diagonally to their left. If the line trace collides with a wall, a second trace is fired in the same direction, but starting from the player's feet, just to confirm that there is indeed a wall that can be run on. Once it's been determined that the wall exists, the two traces are then evaluated and 3 different variables are saved. First, the direction that the player will be wall running in. Second, the side of the player that the wall is on. And finally, the distance the player is from the wall. The wall run direction is calculated by finding the cross product of the wall normal vector and the world upward vector. For the calculation to be correct, the world upward vector must be positive if the wall is on the left side of the player, and negative if the wall is on the right side of the player. The side of the player that the wall is on is calculated by using the dot product of the wall normal and the player's forward vector, and the distance from the wall is simply returned by the previous line traces. These 3 variables will be repeatedly referenced while the wall run is being performed. Moving on to wall run start, the speed at which the player will run along the wall is calculated and stored as stored wall run speed. Stored wall run speed is calculated by taking the player's horizontal velocity and scaling it by the number of consecutive wall runs performed without touching the ground. This ensures that consecutive wall runs will have diminishing speed. The stored wall run speed is then passed into the wall run gravity timeline. This timeline manages the player's gravity scale, setting it to 0 when the wall run starts and then slowly scaling it back to normal over a short amount of time. Now let's move on to the wall run movement tick. This function occurs every frame the player is wall running. The same line traces used in the wall run start function are used again here. If there is no longer a wall to run on, or if the player is falling too quickly, the wall run is cancelled. If not, the wall run direction is calculated and the player is moved in that direction according to the stored wall run speed. However, this movement only affects the player on the X and Y axis. The Z axis is only affected by the player's gravity scale. Lastly, the wall run end function. This function ends the wall run by stopping the wall run gravity timeline and resetting the player's gravity back to default. It also resolves the player's movement state and increments the wall run count variable. Add some animation, camera tilt, and the ability to jump off of walls, and the result is this. Pressing the quick turn button while wall running will cause the player to turn and face perpendicular to the wall, making maneuvers like this relatively easy. With wall running implemented, we can now move on to wall climbing. The wall climbing logic is nearly identical to the wall running logic. It even uses the wall run check function. The only difference is that the player isn't moved horizontally. Additionally, the faster the player is moving towards the wall, the higher they'll climb up it. The player's gravity is also managed by a timeline, though instead of starting at 0, the timeline starts in the negative values, which will cause the player to briefly fall upwards before falling back down. The falling upwards is the actual climb itself. Just like when wall running, pressing the quick turn button while wall climbing will make the player face perpendicular to the wall. This will allow the player to scramble up 2 parallel walls. Currently, the wall climb isn't very useful since there's no way to grab onto ledges, so let's fix that. I want my ledge detection in this game to be very freeform, and the player should be able to hang from most ledges. I'm thinking something like how Peripateia handles ledge hanging, mixed with Mirror's Edge. Now, I should preface this section with a disclaimer. My current implementation of ledge hanging is really buggy and inconsistent, and I'm not sure how to fix it. I'm hoping that some of you watching may be able to help. Starting off, here's how ledge detection will work. Ledge detection occurs whenever the player is in midair and isn't falling too fast. It also occurs during a wall climb. The ledge detection itself occurs every couple of frames. First, a box trace is performed in front of and slightly above the player's head. Should the box trace collide with anything, the Z value of the impact point is saved. Then, a second box trace is performed, this time directly in front of the player. The X and Y values of the hit location are then saved. Combining the two saved transform values, the Z value from the first box trace and the X and Y value from the second box trace, will give us the location of the ledge. The player is then moved into position, and their movement state is set to ledge hang. However, I should note a problem with this implementation. The box trace looks for the Z value of the bounding box of whatever object it hit. This means that if we try to grab onto sloped ledges, this happens. This is a quirk from the tutorial I used when I watched how to implement ledge climbing. I think it's a fairly easy fix, I just haven't gotten around to fixing it yet. For now, we'll just ignore this issue and continue onward. While the player is ledge hanging, they then have 3 different movement options. Pressing the crouch button will make the player drop from the ledge. Pressing the jump button will make the player jump off the ledge if they're facing away from it, and climb up the ledge if they're facing towards it. Dropping and jumping off the ledge are pretty self-explanatory when it comes to their implementation, so I'll go over the ledge climb itself next. First, it has to be determined if the ledge itself can be climbed. This is done by performing a box trace above the ledge. The box itself is around the size of the player's capsule collider. If the box trace doesn't collide with anything, then it means there's room for the player to stand there. The player is then moved to that position, and the ledge climb animation is played. However, if the box trace does collide with something, then a second trace is performed. This trace is in the same location, only the box is the size of the player while crouching. Should the second trace not collide with anything, the player is then moved into position and transitioned into the crouching state. Finally, if both traces collide with something, instead of climbing the ledge, the player will instead jump straight up. And that takes care of our basic ledge climb. There's a lot of logic that I skipped over. Most of it ensures that the transition into and out of a ledge hang is smooth. The animation isn't synced perfectly, but it's so fast that it isn't very noticeable. Perhaps in the future I will go with a motion warping solution instead of this old school approach, but for now, I'm happy with this. When it works. With that, we have a somewhat competent player controller. Sure, there is still a ton of work to be done, but I think that what I have right now is enough to justify a devlog. You may have noticed that I've implemented some basic animations throughout the video. I haven't gone over these because my main focus was on the code itself, though I have ran into bugs with the current implementation, particularly with the ledge hang blend space and the tuck jump animation. There's a lot of quirks with Unreal's animation graph that I still haven't really gotten the hang of yet. I'm particularly confused by the setup of the animation graph for the third-person character template, specifically with how animations are blended between a grounded state and a falling state. If anyone can help me out with this, it would be greatly appreciated. With that being said, I've taken this current build and built a little test map demo that you can all play around in. The link is in the description. Please give it a download and let me know how the game feels to play. Any advice on cleaner implementations for certain features or bug fixes would be greatly appreciated. Take care.